Alright everyone, welcome to the video. We're going to go ahead and change our tactic a little bit for the work that I'm giving you over the Teams and via email. Instead of having you read a document, I'm going to be making videos that allow you to watch instead of read, and then we'll have some either questions from the PDF or some other types of worksheets that you'll need to answer. And that will be how your work will be structured from here on out. Hopefully, I'll be able to make videos for all of the units that we do. You will notice as we go forward that all of the units are review. We are not going to do any new content. So hopefully, if you've been paying attention all year and doing your work diligently, then you will have no problem getting any of this done. So let's carry on. We're going to talk about kinematics today. Kinematics is the study of motion, right? So it's the study of how things move. The quantities that are going to be important in this unit are things such as displacement, distance, velocity, and acceleration. Hopefully none of those are new words for you. Hopefully they are familiar in your mind, and if you remember exactly what they are, then you're ahead of the curve, so good for you. The first thing we need to understand when we talk about kinematics is the idea of a vector. So the idea of a vector is that different quantities in physics can have certain properties, and one property of a quantity in physics is whether or not it is a vector. So a vector is something that needs both a magnitude and a direction in order to make sense. So you need both pieces of information in order for the quantity to be complete. If you don't provide all the pieces of information, then your quantity is not fully defined. So the magnitude is defined as the numerical value of that particular object. And the direction is quite literally the direction. Is it positive, negative, up, down, left, right? So any particular vector quantity, you need a number associated with it and a direction. We typically use the positive and negative x and y direction, so your standard xy plane. And that's what we generally work with. Okay, so the next thing is a scalar. So conversely to a vector, a scalar is a quantity that does not need a direction in order to make sense. It only has a numerical value. So if we're talking about the differences between things as far as vectors and scalars, you can think of a vector as something like a force. So a force requires both a numerical value, 20 newtons, and a direction. So you need to know 20 newtons to the right, 20 newtons to the left, up, down, etc. A scalar would be something like temperature, where you ask, oh, what's the temperature of this particular substance? And you would say, oh, it's 180 degrees, where degrees does not have a direction associated with it. It is simply a numerical value, and that's all the information that you need in order to have a complete picture of that quantity. The next thing we need to know is we need to know what delta is. So delta, which looks like a triangle, it's actually a Greek letter. And what it does is it indicates a change in a quantity. So that quantity is starting at a particular value and ending at a different value. Oh, I guess it could be the same value, and then you would have a delta of 0. But if you put the delta in front of any variable, it means the change in that variable. Therefore, if we put delta F, where F stands for force, delta F would mean a change in force. And specifically, the delta is calculated by subtracting the final quantity minus the initial quantity. So you're going to subtract how much did you end up with minus how much did you start with. And that's going to tell you your delta. So this is going to be kind of rudimentary, very, very basic in a way, but still important. So position is the first piece of information about an object that we can use to determine its motion. So quite simply, position in physics is where an object is relative to an origin point. So it is a particular measurement of where an object is. I mean, there's really no other way to say it. So we're going to use the standard number line generally. Eventually we'll use a coordinate plane instead. But if you're going to define an object's position, that position only has meaning relative to a particular point. So for us in this number line here, when we look at the origin, the 0 mark, everything else, all the other positions are measured relative to that 0 mark. So if here's our 0, we have position 1, position 2, position 3, position 4, and then position -1, -2, -3, -4, because we have defined this direction as negative and this direction as positive. And interestingly, it doesn't actually matter which direction we call positive or negative. We just do it in a standard way to make it easier for everyone to agree and understand. You could, if you wanted to, put positive here and negative here, but we generally don't do that. All right, we're not going to do anything crazy. We're going to work with the standard positive and negative. All right, one quantity that we need to be aware of is distance. So now that we have identified the position of an object, we need to identify distance of an object that has been in motion or is currently in motion. So distance is defined as the total change in position from one place to another. So if you have an object that starts at a specific position, ends at a different position, that means it moved. So the distance of travel is the final position minus initial position. And what you're going to do is you're going to think about it like the odometer on your car. Distance does not have a direction. Therefore, distance is a scalar quantity. All right, displacement. Displacement is very, very similar to distance, but you need to be careful. Displacement is the shortest straight line path from point A to point B. We're going to see a diagram in a minute that kind of clears this distinction up. So displacement is the shortest straight line path from point A to point B. Displacement does have both a magnitude and a direction, therefore it is a vector. The symbol that we're going to use for displacement is delta x. X stands for position, so delta x means change in position. And the unit for displacement, as well as distance, is meters. So let's see a diagram that helps us understand what the difference here is. So I've got two lines, one is squiggly and one is straight. So let's say that we start here at point A and we end here at point B. So let's say that we take the solid blue line path. So we actually physically follow this solid blue line from A to B. Now, there are two ways we can describe this motion. We can say one way that we can describe it is via its distance. So how much distance was covered? And that would be the purple dotted line. So the distance being the total change in position. So you follow along the path and you measure how many meters that path was. Conversely, the displacement is when you look at points A and B and you draw the shortest possible path from point A to point B. So the shortest path between any 2 points is a straight line, So that straight line is something like as the crow flies is one way that people use to describe displacement. So if you could fly straight up into the air, go in a perfectly straight line, and fly straight down, how far would that path be? And that's your displacement. Okay, now we're going to get into the meat of kinematics. So you saw that displacement was delta x, and that was our first introduction to the math and the variables of kinematics. But let's define some stuff. So velocity is a vector that requires both direction and magnitude. We're going to define it as the displacement per unit time. So it's the rate of change of position per unit time. There's a formula for it that I'm going to explain momentarily, and that is v equals delta x over delta t, which can also be expanded into x final minus x initial over t final minus t initial. We're going to get to that in a second. The unit of velocity is in meters per second, m/s, but could also be centimeters per second, kilometers per second, etc. One common unit in imperial units in the America here, excuse me, is miles per hour. So miles per hour is also a displacement per unit time value. All right. So let's look at our formula here, and let's see if we can make heads or tails of it, make sure we're all on the same page. So hopefully this is not foreign to you, but if it is, let's talk about it. So if v is delta x over delta t, we know that delta is final minus initial. So that means that delta x is x final minus x initial. And therefore, similarly, delta t is t final minus t initial. So that's how we end up with v equals x final minus x initial over t final minus t initial. Now, one thing to note as well is t initial is almost always 0. So typically your t initial is going to be right when you start your timer. So right when you start timing whatever it is that you're timing. So your stopwatch is always going to start at 0. There are some cases in which your t initial is not 0, but most of the time you start your timer at the beginning of motion, so your t initial will be 0. It will be relatively obvious when the t initial is not 0, but do keep that in mind. It's not always 0. All right. So the dog travels from 2 meters from his house to 8 meters from his house in 6 seconds. What is the dog's velocity? So we're going to use our physicsy brains to figure this out. And the first thing we need to do is we need to draw a picture. It's always helpful to draw a picture. So the picture that we can draw is we can basically make it like a number line. We are not going into the negatives here. So let's draw a number line with this right here as 0. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So there's our number line. This looks like a little guy over here. That's fine. We need to identify what we're told. So what we're told is that he travels from 2 meters from his house. So that tells me that that is our position initial, 2 meters. So we start here. And then we go 8 meters from his house. So that tells me that is our final position. And so our final position is here. And we do that in 6 seconds. So we're going to call our delta t 6 seconds. And we can do that because our delta t is t final minus t initial, which is 6 seconds minus 0, or 6 seconds. So I sometimes skip the t final minus t initial part, and I just throw the time that the problem tells me as our delta t. You can do this any way that you would like. So the last piece of information has been acquired. So the big takeaways here, we've got this, this, and this. And that's all the information that we need, really, because we're going to go with velocity is delta x over delta t, which is x final minus x initial over delta t. So given that we have everything we need, our final position is 8 meters minus 2 meters over 6 seconds equals 6 over 6, or 1 meter per second. And if we look at our diagram, we can see that that does make sense. All right, so we traveled there from xi to xf. From 2 to 8, that is a distance of 6 meters, right? All right, I suppose a displacement of 6 meters, and also a distance, but velocity is not distance over time, it is displacement over time. So we've got 6 meters, and we do that in 6 seconds, so 1 meter every second. So speed is going to be very, very similar to velocity, but it is a scalar quantity. It's defined as distance over change in time. There is no direction. So if we go back here, technically we do have a direction associated with our velocity here. It is positive. So we would know that if it was negative, let's say if we went from 8 to 2, but we didn't. We went from 2 to 8. If we had gone from 8 to 2, if we would have gone negative, we would have ended up with 2 minus 8, meaning a negative 6. But let's not confuse you any further with that. All you need to know is that when you're asked for speed, it does not have a direction associated with it. It's just purely how fast are you going, regardless of what direction you're moving. The unit is also in meters per second, and any distance per unit time unit is appropriate. All right. Similarly, we're going to move on to the next thing, the acceleration of an object. If you remember back to our forces unit, that's what we started with. I'm doing kinematics in review this time around just because I think it's one of the easier things to work with. I'm pretty sure we're going to do forces next unit as we are here in quarantine. So from the forces unit, ideally you remember how an acceleration occurs. So we should understand that an acceleration only exists when there is an unbalanced force acting on an object. And we have previously defined acceleration as any change in the motion of an object, and that could be both speed and direction. So speeding up and slowing down, those are both accelerations, but also changing direction. That's an acceleration as well. What we need to know as well, if the forces are balanced, there is no acceleration. So if you have unbalanced forces, then you will cause a change in motion. All right, we're going to pause here because we're rounding out on just about 20 minutes. So I'll see you in the next video where we talk about some misconceptions about acceleration. So I'll see you in the next video.